Hi, my name is Rune Haugen. I'm an industrial PhD candidate at the University of Southeastern Norway, and I'm researching the phenomenon of emergent behavior. So what is this? I have this definition. It's a novel system behavior created by interaction effects from parts at lower level, which then cannot be traced directly back down to the constituent parts. So it's like the whole is greater than the sum of the parts, which is a famous saying dated back to the Greek philosophers. So this term has been with us, it has been debated throughout centuries. In the literature, we find three directions within this phenomenon, being someone looks at it as purely unpredictable, others look at it as only predictable, but most and the newest literature includes both these perspectives. So it includes both unpredictable and predictable system behaviors. And to give you an example, we can look at a system from nature. We can look at birds, where we have many individual birds, and they have specific characteristics and possibilities. But how can we explain what we see here in this video? We see here that many birds in a flock, acting as a system, get a new type of behavior. How can we explain this through individual birds? I don't think we can do that. It's like we have to look at the system as a whole and how the different birds interact with one another and how this behavior is then created. We can divide emergent behavior into 4 different categories. The first one is simple, where the behavior is predictable by simplified models of the system. We can intuitively see that this type of behavior can be expected. An example can be that a system uses navigation, utilizing GPS, and when the GPS signals is lost, and the system have to rely on a backup solution like an inertial navigation system, we can expect a drift in navigation. The next category is weak, where the behavior is reproducible and consistently predicted with simulation. This is a more difficult category. It's not intuitive to the human mind, so we have to do simulations to be able to detect it and then understand it. An example can be the range of an electric car, where unfavorable conditions like wind could reduce the range, and different conditions, different combinations of conditions can have such and such effect, and we have to do simulations to really understand how this will impact. And the third category is strong, where the behavior is consistent with known properties but unpredictable in simulation. So here the system effect and performance could be degraded due to unexpected combination of occurrences that is typically not known to us and not intuitive, and we really don't understand what's going on, even though we know the properties involved causing this to happen. The last category, the worst one, is spooky, where the behavior is inconsistent with known properties and impossible to reproduce in simulations. Here we have an example of a system error because of unexpected input resulting in serious injuries or even death, like an aircraft boat crash or car crash. So this is really bad. Emergent behavior is highly connected to system complexity, and we also divide system complexity into 4 main categories. The first one here is also called simple. These simple systems are known. The cause and effect relations are perceivable, repeatable, and predictable. So this connects to the simple emergent behavior category. The next one is complicated. Complicated systems are knowable, and the cause and effect change can be understood by reductionism and detailed analysis. So this is harder to get a grasp on, but it's definitely doable. You have to put in some effort to manage. And this is related to the emergent behavior category weak. The next system complexity category is complex systems, where the cause and effect relations are only coherent in retrospect and usually do not repeat. Although the behavior is consistent and explainable within the system, it is not reproducible, or else it would fall in the category of complicated system. And this category corresponds with the strong emergent behavior category. The last category here is chaotic systems. Such systems often present weird problems and cannot be controlled. And this relates to the spooky emergent behavior type. And it's a type of system with a type of behavior that we do not want. Here we have a visualization of the categories I have explained on the previous slides. The 4 emergent behavior categories and the 4 system complexity categories, and how these relate to one another. What emergent behavior categories are predictable and not, and what system complexity categories that are repeatable and not. And I've also included the distinction between true and false within each category, both regarding emergent behavior and complexity, having to do with the observer knowledge and understanding of the system. So an experienced versus an unexperienced observer might perceive these categories as different, and increasing the observer knowledge will help this transition. So by that we can include also the false, weak emergent behavior in the modeling domain that is understandable by only looking at the model of the system. We have to do simulations to detect true weak emergent behavior, and also false, strong emergent behavior. While we have some residual risks in the upper part with the true strong emergence and the spooky emergence, where it's really difficult or even impossible to detect and understand what's going on. And this separation between true and false will, by increasing the observer knowledge, make us able to transition to a more favorable category. So for false strong emergent behavior, we can transition down to weak emergent behavior by increasing our knowledge. And the same also goes for the complexity scale. Like if we perceive the system as complex falsely, increasing the knowledge may help us transition to a complicated perception of the system, which is of course helpful. Another view to emergent behavior can be this: a separation into unexpected or expected, beneficial or detrimental, giving us these 4 quadrants. And we typically want to move from the unexpected to the expected, detect as much as possible so that we're able to utilize the positive emergent behavior and mitigate the negative emergent behaviors. To give you some more information with examples in each quadrant, starting with the number 1, the normal case, we typically engineer systems to achieve certain behaviors, like when we combine multiple subsystems, we achieve new capabilities, like the system is now capable of flying or sailing or driving. The next quadrant we can avoid by design rules, which is expected detrimental behaviors, where known reduced system effects or performance due to combination of parameter settings or real-world effects, like reduced range or increased planning time for our system, we can now mitigate in design or avoid by operational procedures. The third quadrant is the positive surprise, where unknown increased system effect or performance because of a combination of parameter settings or real-world effects could give the opposite of what we saw earlier, like increased range or reduced planning time. So we should detect as much as possible of these types of behaviors so that we can utilize them. The fourth quadrant is the one we should be most concerned with. That's the problematic case, where system failure due to unexpected input could result in inoperable systems or safety hazards causing crashes, resulting in injuries or even death in worst case. Thank you for listening. Please subscribe to my YouTube channel and stay tuned for more presentations to come.